Welcome to episode 4. Today we're going to run the simulation. We're going to run the robot tasks and we're going to show you how to use the sequencing editor. We're also going to show you how to use I/O statements to coordinate the robots to work together. We're going to run the simulation and we're going to look at the cycle time and we're going to show you some validation tools as well. So here we go. Here's a helpful hint. If you notice, you don't see my robot locations. And that's because what I've done is I went to View and I went to the View modes. And I can turn on and off axis systems and planes. So if my work cell looks too cluttered with all the robot paths, I can turn them on or off using this setting. So it keeps your work cell from looking too messy. Okay, so we've been using the teach interface so far, but there's more to it than just what we've used. This is kind of interesting because some people are experienced with programming robots, and so they're familiar with the syntax. This interface that we use in Delmia, we use this interface on every robot we have. This is a standard interface that applies to all the robots we have in our library, and that's why this is so flexible and has so much information in it. But there's also something called NRL Teach. NRL Teach is using the translator. So I installed the translator in my database, and what it's doing is it's allowing me to teach the robot using its native language. So this is the simulated program that we just wrote, that we've been working with. Only what it does is when you click on a location, the robot goes to it, and then you'll see all these handy pull downs. So if you want to go line by line and make adjustments using the robot's native language, then you can use this interface to do that. So if you're a shop floor programmer, this interface might be more conducive to, or more what you're used to seeing. And so this might be easier. But if you would prefer, this is the standard interface that Delmia uses. And so you have your choice of whichever way you want to program. Or you could use both, and you can just switch back and forth using the native language or using the Delmia interface for teaching the simulation. It's, entirely up to you. Okay, so we have programs in the robot. And each robot's programmed, so what I want to do is I'm going to first validate that I have programs in the robot. So where you should be right now is you have a program in the first robot. And so when I click on that robot task and then I hit the play button, or hit the play button and then pick the task, Delmia runs the robot program. Okay, so that's robot program number 1. Robot program number 2 is for the weld robot. And so I'm going to apply that state and make it active so that when I hit run, this is where it's going to start from. So I click on the weld. I click on the run button, then I click on the weld task, and the robot goes through its weld routine. Okay, so I have 2 programs. Now the question is how do I sequence them? So inside of our sequencing tab, you can see I have 2 separate programs. And these are each individual right now, but I can sequence them in another program and make them run differently. I can make them run in parallel, or I can make them run in sequence. So to get the result I want, I could just create a task and run them both in sequence, and they'll sequence automatically. When the first one's done, the second one will begin. Make sure you make this a nominal task because it is a parent task and it needs to reference the children underneath it. So it must be a nominal task. So when I double click on this nominal task, you'll see that I have tasks that are available to this task. So if I drag and drop the universal robot task and I drop it in this window, and then I drag the FANUC program and drop it in this window, it sequenced them automatically. So I just drag and drop, and then I'm done. So now when I run this task that belongs to the station or the cell, it will sequence them and the universal robot will go, and then the FANUC will weld. So pretty simple to sequence them using this editor. But in the real world, we know that we have a lot of things going on and a lot of devices are actually being sequenced inside of the work cell. So what we're going to do now is we're going to do a little bit differently. Let's get rid of that task and let's just start a new one. And again, make sure that's a nominal task. And I'm going to input a parallel into the program structure. And then I look at all the tasks that are available to this cell task. And now I'm going to drag the pick and drop program under one branch and say OK. Then I'm going to drag the weld sequence and put it in the second branch. So now both of these programs are going to run in parallel, which means that because they're both running at the same time, we're going to need some I/O inside of the robots to sequence them. So the first thing I'll do is I'll create an input, and it's a Boolean, and this is going to be for the FANUC. And I'm going to have to give it a name, something, so I'll just call it I_in. So this is the name of the input to the FANUC. Then I'm going to go to the universal robot. And I'm going to assign an output bool. I'm going to name this one O_out.
Now that we've got the input and the outputs assigned to the robots, now we have to connect them. So we're going to use this I/O mapping editor and map the I/O in the cell. And we're just going to map the output to the input. And we're connected.
So the first thing I want the FANUC to do is wait. So I'm going to input a wait statement, and the condition that it's waiting for is I_in equals true. So I_in equals true is my wait statement. Now I have to make the universal program turn on that output. So at the end of its program, I'm going to drag this output. I'm going to drop it after that last activity and say insert after and say OK. OK, so there's my O_out equals true at the end of my program. So now when I run the program, it's going to throw that output, and then the FANUC's going to execute its program. There's also this I/O monitor where you can dig down into the tree and look at individual I/Os. See, this one's true right now. And then it goes to false when it's done executing. So once the universal robot hits the end of its program, it's going to flip this bit to true. The FANUC's going to see it, and it's going to move along its program. Okay, so see at the end of the program, we turn the bit on in the universal. And also, we can see that we're waiting for it at the beginning in the FANUC program. And sometimes using the sequencer, if you're not getting the results you want, you might not have realized this, but you can teach both the robots at the same time. In other words, right now I have two teach panels open. One is for the universal robot, the other one's for the FANUC robot. What this allows you to do is to interactively click on the statements in each teach panel so you can visually see which line of code is being executed and where that robot is at on that line of code. So, and you can go back and forth from the universal to the FANUC and the FANUC to the universal. And this is a really slick way of being able to sequence these robots visually so you can visually see where you need to input your wait statements or input turning on an output or turning off an output and things like that. So it's a very sophisticated methodology of sequencing a work cell. If you have a lot of devices and you have a lot of robots, it's very sophisticated, and you can create very, very complex programs using everything that we've covered so far.
Okay, so let's take a look at the cycle time of this work cell. So what we want to do is we want to run both the robots at the same time. So here's that task that we created. And when I hit the run button, the cycle time is going to be listed here. Now remember that having it rendered on the screen isn't the cycle time, it's what the software says the cycle time is. 2686. Okay. So there's my cycle time. By the way, this is interactive. If you know there's a collision at, say, 24 seconds, you can type in 24 seconds and the software will show you where the simulation's at that specific particular point in time. Okay, so now let's take a look a little bit deeper and start looking into some of the weld parameters. Do you remember when we established some weld times inside of our arc welding profile? Well, in the TPE arc start command, we have a speed that's designated at 0.008 meters a second, okay? And we also established that on weld tags, that we're going to establish that as our weld speed. So what I'm going to do now is when I created my arc task or my arc operations, these were not applied. And so what I'm going to do is I'm going to show you how to apply these to your weld points. So what you can do is you can go through and individually pick the arc operations that these speeds apply to. So I'm going to click on the arc weld tags and the arc end tags, because as the robot approaches the arc weld tag and approaches the arc end tag, it's going to apply this speed. When it approaches an arc start, it's not on the bead yet, so I don't want to apply the weld speed to that. And keep in mind, if you create your arc operations with the arc profile already applied, it could automatically apply these speeds to it. Okay, so now that we have the arc welding profile assigned to the arc locations, now I'm going to run the cell again. And so what we're going to see here is a significant difference because I've applied the actual weld speed that I want to use. So now we see the robot's moving a lot slower as it moves along the individual seams. Typically, you might want to put in some delays on those arc welding seams. So here you can see it's taking a significant amount of time for the robot to complete the welding task. And that's because we put in a realistic time for the welds. And these arc profiles are going to, you'll have a new arc profile according to whatever thicknesses you're welding, and they will all have different speeds attached to them, so that as you weld multiple types of steel, you'll have different weld profiles to apply. And these get applied at the download for the FANUC. When I hit the download button, these profiles will also be downloaded into that FANUC robot controller on the floor. And so the weld profiles, it's a good idea to have those in step with the weld schedules that they're using on the floor. Okay, so we've got our work cell sequenced and we have it simulating. Let's take a look at some of the tools that I haven't shown you yet. So these are some of the power saw types of tools that'll help you to establish things like robot placement and establish reachability so that your work cell becomes more workable. It's a pretty simplistic example that I have here. We don't see a tip dresser. We don't see a lot of pickups or drop-offs and things like that. But as we know, robots are so flexible that things can get very complex. And so what I want to do is show you some of the tools. I'm only scratching the surface. There's a lot here. So I encourage you to look on your own. But I'm going to show you the reach command. So if I just look at anything that's assigned to this FANUC robot, I want to know if the welds that this robot is supposed to reach are reachable. Because I could move this robot. Somebody could introduce something into the work cell, and then I might have to move the robot. In which case, if I already validated it, I still need to know if I move this robot to a specific location, I need to know that everything is still reachable. So here are all the locations. When I click on the reach and I hit calculate, it changes the color. Everything that's green is reachable. So if I need to move the robot, I can recalculate it, or if I move the robot someplace where it cannot reach it, say at some odd angle, it will interactively change the color of the tag points that the robot's supposed to reach. So if somebody comes to me and says, oh, well, you know what, we need to put something in the work cell to dress the tip of the arc welder, then I need a location for that. And I might need to move the robot to accommodate that. Or if they change it and they say, oh, well, this robot now has to do the material handling and the welding, then you need to know it can reach the pickup, reach the drop off, and reach all the welds at the same time. So this is a really handy feature for you to use. Another thing I'll show you is the auto placement. So you could have a specific area where the robot is, where it's valid to place the robot in the work cell. What I'll do is I'll just size this down and try to get it inside of the fence line where the robot is. And I can modify how granular this setup is just by typing in different values. If I want 10 locations along X or 100 locations along X, I can modify those. And I can also modify the height. I can type in what the height parameter is, so how many millimeters I'm going to raise it up. So I'll say 100 millimeters, and then I'll type in how many layers I want to put in. So I'll have 3 layers, each 100 millimeters apart along Z. And so now I can calculate where inside of this area, inside this volume, can I feasibly place this robot and have it still reach all the locations. And so it'll move along to each individual location and it will represent it with a color. And so green is reachable, red is not reachable, and yellow is questionable, which means that it might be reachable, but perhaps with a different configuration, for example. So as it calculates, when it's done, it will give you all of the viable positions for the robot. So it's pretty slick. It's a very handy tool, especially when you have multiple robots inside of a work cell, and you might not have that much area space. You might not have that many options of places to put the robot in the work cell. Okay, so this next feature I want to show you, this is a cool function that's going to help you with your workflow. As you're processing the robot work cell, you may come across issues that involve a problem that you're having with a tool design or a product design. So I'm going to create a tool cloud. And what this does is allows me to pick individual locations of what I'm welding, and it gives me a representation of the arc welding torch. So for an example, if I have an issue with an interference of the weld torch regarding the product or the holding fixture, I can take a tool cloud and I can export this 3D representation of my tool on that location. So I tell the software what the tool is, and it creates arc welding torches on top of each of these individual locations. So now I can take these and I can raise an issue, for instance. I could take this 3D model of the torches with the control arm and the fixture, and I can raise an issue, have it assigned to a SolidWorks designer, and then they can review the issue and determine if they have a fix for my issue. So it's really pretty slick, and it helps out a lot with collaboration between designers and robot work cell designers.